force of 1 Newton. So I'd say 1 Newton. This cart has a mass of 1/2 kilogram. And if I put in my units then, 1 divided by 0.5 is 2, and then I have a Newton per kilogram. Now, let's apply our unit analysis. What is acceleration supposed to come out to be? Remember, it's supposed to be meters per second squared. So this will be helpful going forward. This tells me then that a Newton, when I bring this to the other side, has the same units as a kilogram times a meter divided by a second squared. And so we're going to use that a lot, especially since we want to end up with an acceleration in the units of meters per second squared. So right here I would say 2, and in place of Newton I'd put kilogram meter per second squared. And then of course I'm dividing by a kilogram. That would cancel off, and I would get 2 meters per second squared. So sure enough, it comes out to be a 2. And the units, and more importantly, is meters per second squared. But watch this. Let me do the same kind of logic. Let me take the plunger and push it a little further in. Now right here, I'm going to get a bigger force. And maybe I'll just draw a line here and say, what would be the acceleration now? Now, this would be a force of about 2 newtons. It's the same object, so I have the same mass. And going through this same calculation, 2 divided by 1/2 is 4. Remembering a Newton here is a kilogram meter per second squared, and so when I divide by a kilogram, the kilograms cancel off, and I get an acceleration of 4 meters per second squared. So again, let me just try to illustrate Newton's second law. It's one that is best described as a calculation. It's the one that gives you the numbers. And so again, the first law tells us, is there or is there not an acceleration? And then the second law gives us a little formula to get to that acceleration. And let's try the little experiment here. So during this time, when I release it, you'll probably see something a little different. See how it got to a higher speed than it did before? Watch, I'll do the small one again. So here's the smaller force. Here's the 1 Newton. And it didn't get to a very high speed. Whereas here is the 2 newtons. And it got to a higher speed. And you could imagine, and if I push it all the way in, and I get even a higher force. So I'll put another line here. This is a force of 3 newtons. And it's still the same object, so it's 1/2 kilogram. 3 divided by 1/2 is 6. And as we did before, a Newton is a kilogram meter per second squared. So if I divide by a kilogram, I will get 6 meters per second squared. So I will end up with a greater acceleration. And you'll see that in the result. When I have a greater acceleration, it results in a greater final speed. And so sure enough, if I release it now, oh bummer. I lost it. Under here somewhere. I was thinking I had left the book. We have a stopper there that I had taken off. And looks like it's still working. Okay, good. So let me place this back on here. All right, so I'll say it again because we're almost done here for today, and then we'll pick up the rest. But Newton's second law is a nice little formula. And part of that is net force. And so more on this tomorrow when we pick up. But I do want to show you one other thing about this before we leave, because I showed you the part that is pretty obvious, I think. More force, more acceleration. And if I can use mathematical terms, we would say these are proportional to each other. That is, more force, more acceleration. And if I double the force, okay, so from here to here I doubled the force, I would double the acceleration. Yep, from 2 to 4. Or this, if I tripled the force, okay, so from here 1 Newton to here 3 Newtons, tripling the force, I would triple the acceleration. So from 2 to 6. And so in math terms, we like to say if you have two quantities on opposite sides and they're both in the numerator, we call them directly proportional. You double one, you double the other. And most people, even if they don't have a physics class, don't need to be told, hey, more force gives you more acceleration. In fact, most people, even without a physics test, a physics class, even guess it right. They would say, oh, double the force. Oh yeah, well then you not only get more acceleration, you get double the acceleration. And that's true, you do. And that's what I want to illustrate. However, what I want to make sure I cover before I finish up here today is don't forget this other factor down here. The acceleration is not just determined by how much force. Maybe you've even noticed this in some very big trucks. I don't know if you've ever been stuck behind a large truck, maybe even an 18-wheeler at a red light, and then the light turns green. And you're probably thinking, oh yeah, that truck, look how big that engine is. That engine puts out way amount of force. This truck's going to just take off like lightning and go really, really fast. And no, I'm sure you're not thinking that. You're thinking the other factor. You're thinking, whoa, 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 whoa. This truck has so much mass. And notice it's in the denominator, and so more mass would actually result in less acceleration. Oh, watch. Let me have the plunger all the way in. Okay, so I got the plunger all the way in. So we're getting a force of 3 newtons. And I'll just show it to you again. If I release it, that's a pretty good acceleration. By the time it gets done pushing, it's going really fast. But what if I did this? What if before I release the plunger, I put one of these, what we call mass bars on there. And each of these mass bars are a half a kilogram. So I just doubled the mass of this cart. But I'm still going to push it with a force of 3 newtons. Will I get the same acceleration? Maybe I'll do the math first. Watch this. I come over here. So my acceleration is, and so I have the net force divided by the mass. And so what I'm trying to say here is with the plunger pushed all the way in, I still have that force of 3 newtons. But now I have a mass of 1 kilogram. I've got the original cart of a half, and then that mass bar I put on another half. And so what I'm going to get is 3, and then the units would be meters per second squared. And so note that that acceleration is not the same, even though it's the same force, because I'm trying to illustrate that the acceleration of an object is not just determined by its force, but it's a combination of two factors, the force and the mass. And so when I release that, you will see that that is not nearly as fast as this. And so this really changes the acceleration. In fact, if I do it one more time, put another mass bar on here, and maybe do the calculation first, I would have a force of 3 newtons again, but now I have a mass of 1.5 kilograms. And so 3 divided by 1.5 is 2 meters per second squared. And so I even have lower acceleration. And so we'll watch it. But I hope what I'm getting across to you, both in the experiment, yeah, look how slow that is, both in the experiment and in the math, is that keep in mind the acceleration, and here's the key word, is explained by, remember that's what this chapter is, explaining motion, where the acceleration is determined by two factors. One is the net force, and the other is the mass. Both of those come into play. Maybe I'll finish up by pointing out then that, again, if I was pulling up to a red light and I saw this massive loaded truck, and even though I know it's got this enormous engine behind it or in it, I also see that it's got a lot of mass. And because of that, I'm thinking, probably has a small acceleration. So I'm going to move over to this lane where there's a small car. Now, small car, I may go, well, small car has a small engine, not much force, but maybe it has a little bit of mass. In fact, I like to finish this part and ask the students, can you think of what vehicle then would have the best acceleration? Now, of those two examples I gave you, this big loaded truck and this small car, you probably would say, well, the small car. And say, okay, the small car has a better acceleration. Now, of course, that's a trade-off because you really don't know how big the engine is. But think about a sports car for a moment. These sports cars that have a lot of acceleration, those things go so quick. Or I should say they accelerate so well because they have a reasonable amount of force. But that's not the real key, is they're often small and light and aerodynamic, and so they have very, very little resistance because of their mass. And that's the big thing. And so I'll ask it again. Can you think of the vehicle that would have the most acceleration? Would it be the big truck, the little car, or the motorcycle? That's really the key. I mean, there's not a sports car around. You could buy a $200,000 sports car and it cannot out-accelerate a simple $1,500 motorcycle. The motorcycle may not have that big engine and it may not be expensive, but it's got such little mass that the acceleration is just over the top. That's why one thing, and maybe the only thing that makes a motorcycle safe, is its high acceleration. Everybody can put on their brakes and you can just go, you can put on late and still stop before all that traffic. You could accelerate forward or back if anything's closing in on you. And so the acceleration is just amazing. Of course, the other unsafe thing is you have no protection around you. So if you do get in an accident, you've got no protection. Well, I think that's a good place to wrap it up here for today. And so we'll call day number 2 on Tuesday done. We're about halfway through chapter 3, explaining motion. And so when we come back tomorrow, we'll pick up right here and we'll begin to talk about Newton's third law. Oh, before even that, I got to say a little bit more about net force. And then we'll get into the third law and wrap up the chapter and start the next one. So, good luck. Work on the homework for chapter 2, and I'll see you tomorrow.